Okay, here's another example, and this one's going to use the results that we got when we did something similar with the electrostatics example, where we was finding the force from a line of charge at point P. In this case, we're going to find the electric field at point P, and it is quite a useful example because it's going to use the results we got. Now, because we've calculated the force at P, we've already got an equation there, so there's a clue to help you with this question. So if you go back to that example, you'll be able to use that equation, and you might, with a bit of luck, be able to solve this, and you should be able to figure out the electric charge Q along this bar along a line of length 2a. What is the electric field at point P? You should be able to easily figure that out, yeah. So if you just go back over that example, if you remember it, if you copied it down in your notes or whatever, then this one will be quite easy to work out. But it does leave an interesting the nice thing with using the field here, it's a nice follow-on from the force, is it actually shows something quite interesting at the end. So let's go through it. So here we are. So what we're trying to do is we're trying to find the electric charge Q, which is a whole bunch of charge along here, okay, along a length of 2a, so that's 2a, remember this problem, and we want to find what the field is at P. We encountered the same situation on the video on electrostatics, and looking back at that solution for the force F, so when we found the force F at P, we see that the electric field E at P is just equal to, so remember the electric field really is just simply equal to F over Q, yeah? So once you know it's F over Q, then you can bring back that equation that we got in that example. Remember when we did it for finding the force, we ended up with an equation like this. So what I've done here is I've just divided the force by Q, and the Q cancel with that original equation that we got on that example. So we've got that. So there's no need to go through the whole thing again. When x is much larger than a, this becomes approximately 1 over 4 pi epsilon q over x squared in the I direction. Okay, so the resultant is going in this direction. So this is the field of a point charge q at distance x. Okay, and so we can use that for this. Okay, right now, given this, we get an added dividend from this equation here if we express it in terms of the charge per unit length. So the charge per unit length would be this charge, and we could divide it by 2a, and that would give us the charge per unit length. Okay, so and that was the total length here, yeah. So if we divide the charge by 2a, we're going to call that the linear charge density. We'll call that quantity. So have I done it here? Yeah. So charge per unit length, q over 2a, we'll call it linear charge density, lambda. So substituting q equals 2a lambda into equation 1. So if we put that in here and simplifying, we'll get this. So if we rearrange the equation, in fact I've given you a little clue here about how you get this bit here, yeah. So you can just look at that and see how that's done, basically. What is E at a distance x from a very long line of charge? To answer that question, we take the limit of equation 2 as a becomes very large. So we're going to let this little a underneath here become very large. In this limit, the term x squared over a squared in the denominator becomes much smaller than unity, and so we can imagine as a gets very big, this just goes to 0, yeah. So then if that goes to 0, then we've just got the square root of 1, which is 1. So we end up with this. So as a gets much greater than x, we end up with, in other words, if the distance, if this line of charge is infinitely long compared to the distance x here, okay, then we can write this down. We can say that the field is equal to the charge the linear charge density divided by 2 pi epsilon naught over x. So at any point P at a distance r from the line, the field has magnitude E over lambda over 2 pi epsilon naught r. Its direction is radially outward from the line, thus the electric field due to an infinitely long line of charge is proportional, now this is the important point of this, is proportional to 1 over r rather than 1 over r squared as for a point charge. So that's kind of interesting.